Okay. Good afternoon. My name is Trevon, and I'll be giving my presentation on next generation solutions for modern network attacks. So, who am I? I'm a graduate student at UNC Charlotte. I'm a security enthusiast, and I'm also a member of the 49 Security Division. So, because I'm a graduate student, a lot of my presentation is going to be a little bit forward thinking, research based. Uh, so, I think it should be interesting for you guys. Okay, so when we think about attacks, common network attacks, there's the mixture of thinking about how attacks happen and then how, the entry points of attacks, what the effects, the artifacts. So a good way to think about network attacks is you can think about malware as it's propagating through a computer network. You can think about ransomware as it's also propagating and locking computers. You can think about phishing emails, targeted attacks that are the basically the first step of some type of initial presence of an attacker inside of a network. And then you can also think about DOS, denial of service attacks. So what are kind of the current approaches to mitigating these types of attacks? Or what is the common knowledge for mitigating these type of attacks? The conventional wisdom of Twitter says to just use Linux. I really thought this tweet was funny, so I wanted to include it. But it's not really serious. You can't just use Linux and avoid network attacks. But what you can do with conventional wisdom is deploy some type of endpoint software on your laptops. Think about antivirus. Think about endpoint protection systems that are kind of correlating these events happening on your system and then kind of propagating it to some security information management system, and then that's changing policy based upon what it sees happening in the network. That, depending on the maturity of the I guess you could say enterprise or business, leads to either a robust edge security system with next generation firewalls, which kind of marketing for including packet filters that are able to do deep packet inspection on the packets that are flowing into the network and filtering out 0 days as they come into your network. There's also the basic general wisdom of the field following best practices to be able to stop these attacks. You don't necessarily have every port open. You only have ports open that you need. Your network is segmented. You're leveraging authenticated access and zero trust. Zero trust, I think, is a current approach, and is also like one of those approaches that's still being defined and outlined and improved. You can also educate your users. I think there's a big discussion. You could say maybe it's not a big discussion in security, where it's like, oh, we should be able to protect enterprise networks without user education, or we need the users to stop making mistakes. User education is important. How important? I think it depends on the person, but it is also part of a way that you can mitigate attacks. So, more forward-facing, forward-looking, what are the trends we see kind of security software going towards or trying to include in terms of marketing or just like in terms of specific technology? We see the introduction of machine learning and artificial intelligence specifically for deception, trying to deceive attackers of assets that are in environments that are not actually there, but then also using machine learning for advanced measures of detection, being able to find patterns, anomalies in network traffic to be able to stop those specific attacks. We also see advancements in automation. VMware acquired SaltStack like 3 years ago. So automation is important to these industry providers and how they're integrating it into their stack, how they're allowing you to automate the provisioning, the reprovisioning of your assets based upon what's affected, what's not affected is a very much active area of development and research. And like I said earlier, zero trust architectures are still kind of being well defined, being improved. So that's kind of like a big area of the security, what's it called? Field is trending towards. And then there's also the diversity of solutions. The NSA put out the best practices guideline for networks, and essentially it was used a bunch of different firewalls, use a bunch of different switches. Don't use the same thing, because if you use the same thing and it gets hacked, then your whole environment's basically going to get hacked pretty easily. And then the other trend is move everything to the cloud. I'm not going to have much comments on that, but that's kind of what it seems to be. People are offloading security responsibility to cloud service providers, and realizing that cloud service providers also have to have best practices when it comes to security, and you have to make sure that you tune your access controls correctly so that you aren't on the other end of a data breach. Okay. So there are some shortcomings, and I think this is a generally true shortcoming for the field of security. Is you take a non-security person, you say like, these are all the great things that you can do to protect yourself, and they're just like, oh, this security function, this antivirus, slow down my computer, this firewall, next generation firewall, slow down my network. I have a gig network, and it's forcing me to have 100 bit speeds. There's no reason for me to pay for fiber if I'm only getting 100 megabyte speed. So I just disabled it because I wanted the usability. And in some ways, that's kind of generally true for where we are in security. So how can we kind of improve the trade-off math of network security solutions? And this is kind of the meat and potatoes of my talk. And that requires us to think about what are the base level improvements, what are the base level places where we have room for improvement. And that's really kind of like the network stack. How we deploy, how we think about the network is changing in terms of network design, and it's slowly propagating over to security. But the idea of software-defined network is being leveraged by a lot of security researchers, and to kind of take a step back and think about software-defined networking. Software-defined networking is this idea that you can decouple the control and data plane. Traditionally, before you have SDN controllers introduced into the environment, you're using routers. These routers are communicating to each other, saying, hey, this computer's over here to this router, so that the packets can flow within the network. Routers are also connected to firewalls. In the software-defined network architecture of the network, you have the network controller, having this global view of the control plane, where it doesn't necessarily have to communicate to other controllers unless you're maintaining this internet-wide network, which allows you to basically, as the controller, communicate to switches directly, not to other routers, that you want to move this packet here, or there's a better path a better path that has less congestion, essentially. And so what this basically enables is the introduction of data plane programs. Good way to think about data plane programs is to think about eBPF, which is the extended Berkeley packet filter that we see in Linux, which basically allows you to write programs that hook into kernel drivers, and they're basically really fast programs that do this inline processing of data coming in, providing observability, but then also you see eBPF used in packet filters like IP tables, et cetera, et cetera. So this has the potential, using in-network security on switches, has the potential to handle the expensive part of parsing or implementing functions of packets that are in flight within your network. So it's important to think about in-network security being the ability to take this idea of eBPF, hooking, not necessarily hooking, but having a program within the pipeline of a switch to be able to do some parsing, some checking of packets as they're propagating through your network. So some examples, because that was a lot of information. There's only 3 bullets. Talk to me. Okay, so there's some helpful patterns to understand when it comes to implementing in-network security. One, the protocol. The protocols are very important. And one of the protocols that we see leveraged the most in terms of research is DNS. Why DNS? Because since the beginning of the internet, when they realized that a phone book for the internet for websites was important, one of the implementing requirements of DNS is that it has to be clear text, it has to be fast, and it has to work. So because DNS is clear text, it's fast and it has to work. That means that everything can see DNS records. You can have switches see DNS records. There is no TLS to protect it. I mean, of course, there's DNSSEC, right? But there is no encryption for DNS. Now, DNS also has a lot of attack vectors. We see a lot of DDoS attacks that leverage DNS, and we also see DNS cache poisoning attacks. Interesting enough, those attacks are very bad in terms of networks. I guess network security posture. So to understand kind of the opportunities for implementing network security functions, you have to kind of understand like what are the contents of your packets. Can your switch even see packets, right? If you have a TCP packet and it's TLS encrypted, there's no way that you're going to be able to do any, cool jazz on your switch for those specific TCP packets. But if you are trying to stop DNS attacks, yeah, you have a great opportunity there. So to understand kind of some DNS attacks, I mean, I'm sure everyone is familiar. If you're not familiar, there was a really big DOS attack using a botnet, the Mirai botnet. I think I'm saying it right. Basically, is leveraging this protocol to take things down. But to take a step back and to better understand DNS attacks, there's DNS reflection attacks, and there's DNS amplification attacks. Basically, both of these are leveraging behavior within the protocol. And specifically for the DNS amplification attacks, you're leveraging sending packets to a DNS server and then getting a larger response from the server, redirecting that to another machine. And now you have thousands of multiplicative packets going to that endpoint machine than you send to that machine. There's also, these volumetric types of DNS attacks in a similar type of vein that leverage non-volumetric, meaning that it's abusing behaviors within the protocol, similar to the amplification attacks. And then volumetric it's literally just spamming a user. And once the user's resources cannot continue to expand to handle that traffic, it basically just, keels over and can no longer do anything. It can't even provide, usability to users. Okay. Then another type of attack is cache poisoning. So there's this really advanced paper that was published in Usenix, Usenix 32, outlining how you can abuse cache poisoning on conditional DNS servers, which basically are, forwarders and resolvers. But the basic idea to know about DNS cache poisoning is like, in a cache poisoning attack, you're essentially trying to get the forwarder to think that google.com actually points to whatever malicious domain that you have access to. So what this basically enables is an attacker to redirect users to malicious sites that they probably shouldn't have been redirected to, and also provides the ability to disrupt services that you probably don't want to have disrupted. So there's a lot of different examples of how these attacks are able to be implemented. There's a lot of discussion about how most of the major DNS service providers and even unbound bind servers that could be implemented in-house were all vulnerable to this type of attack, which is abusing the DNS protocol. So going back to those helpful patterns, so DNS is an open protocol. It is abused by attackers every day, honestly, for exfiltrating, but then also, for setting up persistence inside of environments. There's a lot of different attacks. Main attacks that I covered were DOS and DNS cache poisoning attacks, and then the opportunities for parsing these packets for security specifically relies in the openness of the DNS protocol. So when it comes to implementing in-network security, there's a couple of things that you kind of have to know. One, you have to be able to do some type of data plane programming. And so to do data plane programming, in my research, I've been looking into P4. P4 is this language that allows you to write how you want your switch to process packets. So you can say, hey, You see this DNS packet, I want you to handle this DNS packet this specific way. You see this Modbus packet, I want you to handle this Modbus packet a specific way. TCP, UDP, I don't really have the ability to do that, so I'm not going to do that. You can define all of those actions within P4, and then you can deploy it to a switch, and you can communicate between your switches and P4 using P4 runtime. It's all really cool. And there's a foundation behind it, the Open Networking Foundation, that's continuing to develop on top of this platform. So once again, it allows this inline packet processing of whatever, predefined functions that you deploy. And then it also provides this opportunity to bring balance to middleware. You don't have to forward packets to this appliance, and they're doing all this cool jazz within the appliance and then forwarding it to the end host. Like, for example, Snort, sending all your packets to Snort so that Snort can do deep packet inspection, do some signature analysis. You don't necessarily have to send it all to the middleware appliance. You can now, think about how can we balance what middleware does and what you can do with these low-level functionality within switches on the device. So what are the performance differences? Why is in-networking security important? This is the meat of the potatoes, right? So if you were, this is from a paper called P4 DDPI, so it's P4 DNSD packet inspection. And what in their paper, what they're essentially doing is they're taking this idea that, hey, we can use P4 to extract all the domains from records in DNS records as they're passing through the switch, because we can see them. And then we can basically forward them to this access control list. We use access control list every day in firewalls, and say, is this URL part of this access control list? Yes or no? If it is, we can drop this packet. If not, we can, allow it to propagate through the network. And this is comparing its ability to stop a DNS cache poisoning attack versus pfSense. pfSense, is kind of representing the send everything through one kind of machine. And so what we see is that in terms of like packet delay, as you increase the packets sent into the network, with pfSense, of course, as you're increasing the amount of network traffic sent through it that it has to process, eventually there's going to be delay that's kind of incurring. But with this program on switches, you aren't necessarily seeing this rapid growth delay. Like there is no delay with the growing amount of packets, which is a really good feature to have. In terms of packet loss, people commonly don't like, for example, using VPNs, because sometimes when you use a VPN, you have like this weird jitter, and then if you're watching a video, the video starts buffering, and then it's just like, what happens to the video? Do I have to disable this VPN or no? Similarly, pfSense, when doing DNS record resolving, trying to parse and filter out these records, it starts to lose packets over time the more packets it has to process. But with this program in switches, there is literally no packet loss. So that means that you can, essentially implement these kind of rudimentary access controls within switches and have the same performance as you would as if you didn't have these security functions enabled. Users will not necessarily, notice that, hey, there's a security function enabled. So kind of looking forward to, what is the future of in-network security? So like there are a lot of great opportunities, there's a lot of great potential, but it requires, an understanding of these protocols, these underlying protocols. How can, we leverage this type of thinking in network security to offload a lot of packet, what is the word I'm trying to think about? Packet parsing without, doing all packet parsing on the switch. And that's kind of where I'm at from my research. How can we make more generalized solutions that, take trade-offs, right? We're using the switch for more processing in the packets, and then sending these already processed packets to some middleware appliance to do the rest of the processing, to reduce latency, to reduce packet loss, but then also to increase the robustness of network securities. It also kind of requires this deep understanding of how to compartmentalize functions. You wouldn't necessarily want to try to extract every DNS record from these DNS packets because, as the paper shows, there's a limitation of how long of domains you can extract. So if, in this cat and mouse game of security, people are going to eventually realize that, hey, you can just create a domain that's 64 characters long, send it into the system, and we still have the same cache poisoning attack. It doesn't stop the attacker. But with a good balance, you can introduce the ability to, one, extract and decouple these packets and then send it to an appliance to be able to get the benefit of a trade-off of speed without the packet loss. So those are kind of the things that kind of want you to take away from this talk. So in conclusion, you can find me online. I post my research. I have a personal blog where I sometimes post my research security talks, and then I have a more academic blog where I post papers, teaching stuff. And then I'm on Mastodon. I'm on Twitter. Not really on anything else, but I have an email, and that's my talk. Thank you.